All right. Welcome all to this week's UTIG discussion hour. Today our speaker is Zach Sickmann. He's a postdoctoral fellow here at UTIG. Prior to coming here, he received his PhD at Stanford and his bachelor's from Trinity University. His research interests include detrital sedimentary systems, basin analysis, tectonics, sedimentology, and probably lots more that I don't know about. And today his talk is titled Thinking About Sand Mining from Source to Sink. And so I'll let Zach take it away. And then just one thing to note is that Zach mentioned that it's totally fine to ask questions mid-talk. You can type it in the chat and hopefully we will see it. So take it away, Zach.
Great, thank you very much. Yeah, so I've got this chat box open in the bottom left of my screen. I'm happy to keep it an open discussion. I mean, I'm really talking about ideas as much as anything, you know, particularly technical. Okay, yeah. So what I'm going to talk about today is kind of some work that I've been thinking about with a number of collaborators about thinking about this issue of anthropogenic coarse sediment extraction from a basin analysis perspective. From the perspective of kind of including these human sediment dispersal pathways and human sedimentary sinks into a broader kind of system scale understanding of the new kind of human basin source to sink cycle. And so specifically, a lot of what I'll be showing is part of this review that I'm working on with Dr. Aurora Torres, who was involved in a lot of kind of the early work in defining kind of the quote unquote sand crisis as a major sustainability issue that needs kind of increased attention, particularly from communities like the siliciclastic sedimentology community. Okay, so I'll start with this image. This is the Lapis Road Cimex sand mine. It is the last beach sand mine in California. It's scheduled to close pretty soon because it's messing up the beach. So what you're looking at here is, this is a little platform, a little floating platform that's got a little hose with an agitator that goes down and agitates the sand and then sucks it up into a pipeline that deposits it kind of back here, where it's then shipped off down the highway to the plant that processes it. But entirely coincidentally, this sand mine sits right in the middle of one of the study areas that I worked on during my PhD. So I do basin analysis. I do a lot of provenance analysis, and I designed this study to look at the way that sand mixes in the littoral and submarine canyon environments, and how that might be controlling the way that provenance signatures are expressed across a sediment dispersal system. And when I started this project, like I said, I didn't know the sand mine was here. But we started to get these results, particularly with respect to the composition of the sediment that we were seeing down Monterey Canyon, that started to suggest to us that we might be seeing a detrital record of this anthropogenic sand extraction from this system. And so during peak extraction, sand mines in the southern part of Monterey Bay we're extracting somewhere on the order of 200,000 to 300,000 cubic meters of sand per year. And this is equivalent to about 30% of the total coarse grain sediment budget for this dispersal system. So as you might imagine, you know, this is a pretty major perturbation. And not surprisingly, it's leaving a record. And basically what we saw, just to summarize this, was the sediment in the upper part of Monterey Canyon is much younger than the sediment in the older part of Monterey Canyon. And so we saw this compositional shift in sand from the upper part of the canyon that was suggesting anomalously high input from the northern area that was not being subjected to this sand mining perturbation. Whereas in the lower part of the canyon, we were seeing what we would more expect from a natural signal. And so this was interesting. We wrote a paper on it, but it got me thinking more generally about how one might apply basin analysis, source to sink, sediment dispersal concepts to understanding and addressing sand mining and anthropogenic sediment extraction more specifically. So what I want to do here real quick is just establish some kind of concepts with respect to the ways that humans perturb modern sediment dispersal systems. And so there's actually lots of literature on this about how do you define the Anthropocene, the number of ways that humans are messing with natural sediment dispersal systems and the volumes associated with this. But you can basically break down the ways that humans are perturbing natural sediment dispersal systems in the modern into these kind of 4 areas where they're generating sediment, strip mining or excavation. That's an anthropogenic mechanism to generate new sediment. Impounding sediment, largely generally behind dams, and this is a pretty major source of decreased coarse-grained sediment flux, in particular in modern sediment dispersal systems. They redirect and redistribute sediment. So what we're seeing here is a satellite image from the Ganges River, which is an area that I'm going to talk about in a little bit more detail. Sorry, y'all, there's timings associated with these slides, and I don't know how to change that. So I'm just going to have to keep jumping back and forth occasionally. But anyway, so this is a cutter dredger. And so it's cutting a shipping channel through this sandy area in the Ganges. And then finally, extracting sediment. So permanently removing natural sediment from natural sediment dispersal systems and putting it into new human sinks. And so the reason that I like this image and illustrating this specifically is that it shows this cutter dredger cutting this channel, and it shows this repository of sand that it's piping into the onshore. But what it also shows, you see these dump trucks here, they're removing the sand from older generations of this channel dredging. And you can see, if you look at a time series in the historical imagery in Google Earth, you can see that this is a cycle that repeats every year. So there's 3 or 4 of these cutter dredgers on this particular stretch of the river. They cut a new channel every year. Sometimes they put the sediment that they're dredging into kind of other active riverbank or river bars that are in the middle of the river. That's fine. They're just redistributing the sediment, but it's still in the system. And then other times it's being put in these repositories that are leading to permanent extraction of sediment from the system. And so specifically what we're going to be concerned with and what I'm going to be talking about today is that permanent extraction, that permanent anthropogenic extraction of sediment and sequestering of natural sediment into built environment or human sinks. So I'll talk kind of generally about 4 different questions here. Why is sand and gravel mined? How much is extracted from natural systems? How do we estimate how much is extracted? How does it compare to natural supply? What does sand mining in an active dispersal system look like? What are the local effects, system scale effects? How might we better study it? And then talk about some concepts about carrying this work into what I'm going to call the human basin. And what I really mean is just the built environment, human sedimentary sinks. And so, each one of these questions, answering each one of these questions is not trivial. And so what I'm going to talk about is as much thinking about how we're going to go about addressing these questions and getting any input that you might have, as much as it is me providing answers to these questions necessarily. So the first question, why is sand and gravel mined? Well, there are a number of reasons. I mean, they put it in golf course bunkers and playgrounds and such. But by and large, it is mined for construction materials, and the majority of that is put into concrete. So concrete is 1 part cement, Portland cement, which is itself made from limestone, heating up limestone, fluxing some other stuff through it, generating this powdery material that when it's hydrated becomes the cement to concrete. And then the volumetric, the matrix of the material is aggregate, what the industry calls aggregate. And so that can be crushed rock, or it can be simply natural sand and gravel. So this is just kind of a backyard demo that I did to illustrate this on a very local scale. I just went to Home Depot, got a bag of quickset concrete, washed all the Portland cement out. And this is the aggregate. This is the matrix of that concrete. And so, I bought this here in Austin. And what we see here is this kind of quartzo feldspathic sand and these kind of pebble-sized crushed limestone grains. So, what we're seeing here is natural sand, probably mined from somewhere on the coastal plain here in Texas, and then crushed limestone, plenty of limestone around here. So by and large, the fine aggregate in particular in concrete is natural sand. Now, the coarser aggregate is often crushed rock. The notion that anthropogenic extraction of sand and gravel from sediment dispersal systems is a major sustainability issue is nothing new. This has been recognized for a long time, and particularly, in the US and Canada and most of Western Europe, a lot of this aggregate material is now provided by crushing rock. But in a lot of the rest of the world, this is not true. It's still natural sand and gravel. And even in the US, Canada, and Western Europe, the finer aggregate portion is usually still natural sand. So what are we looking at here? This is not great to scale, but it just kind of illustrates the various types of aggregate that are extracted. You got this like more decorative river rock that people use in gardens and such. But for the more industrial uses, we're looking at sand, and then in this case, this is crushed rock. So we're looking somewhere in kind of the mid to upper very fine sand range into the kind of medium pebble range. So what we're looking at is relatively coarse sediment. And that's going to be important when we start thinking about things like natural sediment supply, and what the kind of finite or sustainable resource here might actually be. Okay, so how do we estimate how much is being taken out of natural sediment dispersal systems? And this is kind of a can of worms that is very difficult to address for a number of reasons. Not the least of which, what I'm going to talk about in just a second, is that virtually nobody tells you how much sand they're taking out. There are some national quotas for some countries, but we're looking at an example here, like I said, on the Ganges River in northwest Bangladesh and into northeastern India, and I can just about guarantee that nobody is quantifying, at least in a regulatory way, exactly how much volume of coarse sediment is being extracted here. But that's not to say that we can't get some numbers. So the USGS does report sand and gravel extraction volumes for the United States. I know it says crushed rock here, but this is just sand and gravel. I cut off a whole paragraph that explains other aggregates above it. And as does Canada. So the US and Canada extract, just south of 700 million cubic meters of sand and gravel every year. Of course, a lot of this is from what the industry calls fossil deposits, or what we would just maybe call older deposits in an older sedimentary basin. But a lot of it is still coming out of active sediment dispersal systems, even in countries like the US and Canada. So although very few countries report sand and gravel extraction volumes explicitly, 150 countries report cement production. And so we can use this as a proxy to estimate the amount of aggregate material that would be required to make concrete from that cement. So about 95% of cement that is produced is used in concrete. There's some other uses like decorative stucco and stuff like that, but the vast majority of cement that's produced globally goes into a concrete material that requires an aggregate material as its volumetric matrix. So if we do some quick math here, we ran the numbers for 2019 because we didn't want to mess with 2020 numbers, although they are available. So somewhere north of 4 billion tons of cement are produced globally by these 150 countries that report cement production every year. And so through some math, judging that concrete is 7 parts aggregate to 1 part cement, and using a density of 1.77 tons per cubic meter for kind of representative aggregate density, we can estimate that global demand for sand and gravel, or we should say all aggregate, and then ultimately working on hopefully trying to quantify how much of that is natural sand and gravel going forward, is north of 15 billion cubic meters of this material on a yearly basis. So when we start to think about comparing this to natural supply of sediment, basically how much new sediment is produced on Earth every year. And I guess I should probably back up here for just a second and say that there are very specific material properties that the aggregate that goes into concrete are required to have. The example that's always brought up in talking about this is, why don't they just take sand out of the Sahara? There's a specific grain size. It has to be coarse enough, and crucially, it also has to be angular enough. And so a lot of times Aeolian sand is too fine and too rounded. And that's why a lot of this extraction comes from rivers and comes from beaches, relatively immature sediment. It is of the right grain size distribution, and it is of the right angularity to form a matrix that kind of interlocks together. As you could imagine, very rounded grains don't provide a great matrix for this in terms of resisting shear. Okay, so anyway, in thinking about what is the natural supply of sediment that we can put these volumes into context with, there are some very crucial distinctions that we need to make with respect to the type of sediment that we're looking at here. And that is the difference between total sediment load, suspended sediment load, and bed load. And so we're looking at the upper range of very fine sand into kind of the mid-range of pebbles. And so although in the lower parts of the fine aggregate grain size distribution down here, we are probably looking at material that spends a not insignificant time in suspension, by and large, we're looking at material that is being transported by bed load processes. And so that distinction becomes very important when we start looking at natural fluxes, natural loads, because suspended load is considerably easier to quantify and model than is bed load for a number of reasons, not the least of which is that you can put some sediment traps or you can use some acoustic monitoring methods to get at kind of relatively continuous records of suspended load in a river, while generating quantitative assessments of what the bed load is doing requires more difficult sampling methods or some kind of other remote sensing methods that are continuing to be developed, but the data is not available for most rivers in the world. Although suspended load data is available for a lot of the world and has been for quite a long time. So that leads to one of the first things that we wanted to address in the review that we're working on currently, and that is addressing this common shorthand comparison that annual global sand and gravel demand is 2 to 4 times greater than what rivers produce. And so the numbers that you're using here depend on what you're talking about. They depend on whether you're looking at total aggregate demand, whether you're looking at sand and gravel demand. So putting this in context, specifically what we're concerned about here is sand and gravel demand against natural sand and gravel production by the world's rivers. And so, all of this gets conflated. A lot of the literature written on this subject is written by people who are maybe more invested in the ecological side or on the policy side. There aren't necessarily a whole lot of process sedimentologists writing these big global reviews. So that having been said, the citations that are often used here are the classic kind of Savitsky and Milliman, or these papers on global sediment flux to the world's oceans, which almost exclusively report suspended load, or they report total load and they acknowledge that it is almost exclusively suspended load that they're talking about. So these citations are very interesting and they're very useful, but with respect to thinking about sand and gravel supply versus sand and gravel demand, they're not really comparing apples to apples here. So we're working on various ways to improve some of these numbers. Not that we're going to do Savitsky level modeling here, but a better number to use here is about 847 million cubic meters of bed load sediment produced by the world's rivers on a yearly basis, which is at least 20 times the potential sand and gravel demand for concrete alone. So one of the things that we kind of always talk about here when we start to dive into some of the numbers is that it's actually worse than people are saying. They use these numbers that try to describe how bad it is. And they're describing it in a way that's actually an order of magnitude better than it actually is. So anyway, that's just an interesting distinction here. Okay, so let's put some of these numbers in natural system context. So what we did here is we went through various literature sources. Some of these we kind of back of the envelope calculated ourselves based on isopachs and previous work in the areas. So I'll just show kind of the coarse grain sediment budget or the bed load produced by some representative rivers that span a couple of orders of magnitude. And then ultimately we'll compare them to some known demand volumes. So these three here on the left are kind of small mountainous rivers in California. The Salinas River is the classic small mountainous river that Milliman and Savitsky talked about in that paper. So their kind of coarse grain budgets range somewhere from 40,000 cubic meters to a couple 100,000 cubic meters per year. The Mekong River produces a couple million cubic meters per year, as does the Mississippi, approaching something closer to maybe the 10 million mark. Kind of going up some orders of magnitude here. Just for note, the total coarse grain sediment budget for all of the California coast is on the order of about 3 million cubic meters per year. The budget for Indonesia is, what's that, approaching 100 million, as are some of these various other features, including the modern Bird's Foot Delta of the Mississippi, the entire Ganges-Brahmaputra Delta. You know, we can talk about how we calculated this, but we basically backed it out of an isopach. And then we get into North America, Asia, and then finally the annual global bed load, which, as I described, is about 847 million cubic meters per year. Okay, so let's put that in the built environment context. And again, remember, these are kind of the new human basin sedimentary sinks that are receiving some of this material. Average school or hospital is about 13,000 cubic meters per year, or you could build one hospital with, or you could build 2 or 3 hospitals with one small mountainous river. This is that volume that was being extracted from Monterey Bay on a yearly basis. The Burj Khalifa, the tallest building in the world, is about 300,000 cubic meters. And then there's some record of mining on the Cape Coast in Ghana that is suggestive that it's about equivalent to what was being extracted in California. Thinking about larger infrastructure like dams, I mean, those are the real sediment sinks in the built environment. The Hoover Dam in the U.S. required about 1 or 0.8 to 1 Californias, roughly a couple million. All of the sidewalks in New York City have about 4 million cubic meters of aggregate material, potential sand and gravel. The Three Gorges Dam in China is just about the largest concrete structure in the world. And it required, I think the number is like 19 million. And then we get into US and Canada production, which you will note exceeds North American bed load by a significant margin. And then we get into the really big numbers here, the global demand for sand and gravel, which recall is that kind of just north of 15 billion. Okay, and then these are the kind of interesting numbers here, at least to me, where we start to get into a little bit more of the civil engineering side. So potential sand and gravel in all US infrastructure and potential sand and gravel in all Chinese infrastructure. I don't remember off the top of my head what the specific number for this US infrastructure is, but for Chinese infrastructure, it's about 85 billion cubic meters. And so the way that we calculate this is there's something in materials flow analysis called the in-use stock. And it basically describes the volume or the tonnage of the in-use portion, basically active, how much of any given material is sequestered in active infrastructure at a given time. And about 10 years ago, that number for China equates to about 85 billion cubic meters of sand and gravel, potentially sequestered in concrete, or based on our calculations, a couple of hundred years of coarse sediment deposition on the largest delta in the world. Okay, so that kind of gets at like the volumes that we're looking at here, and kind of comparing supply and demand. So let's talk about what this actually looks like in an active sediment dispersal system. And so this figure kind of illustrates the different ways that coarse sediment is extracted from natural deposits. Mined in, say, a floodplain. This is meant to represent active bar mining, and you'll see why in just a second. Mining from old alluvial plains, or mining from ancient basins, or dredge mining, so on and so forth. And what we've kind of shown schematically here, following some previous work, is just kind of a schematic representation of the sediment residence times in various of these places. And so the sediment residence time is going to become particularly important when we think about the timescales of sustainability. Are we taking a grain of sediment out of a point in the system that was immediately destined to continue down system? Are we taking a grain of sediment that was destined to stay maybe for 1,000 or 10,000 years there before moving down system? Or are we removing material that was actually kind of permanently deposited there and was no longer part of our source to sink sediment dispersal cycle? Okay, so what I'm gonna show now is just some images of some mapping that we did on this stretch of the Ganges River in northwest Bangladesh. And so our goal here wasn't to really quantify the total volume that was being extracted. Our goal here was to kind of show some representative examples of what sand and gravel, in this case really fine sand, because the Ganges River is very much dominated by fine sand, extraction looks like in a modern system, and use some of those numbers to kind of make broader statements about the implications of extracting sediment from such an active system. And so what I've shown here in this first image is actually part of the sand mining apparatus of the river that we don't really have a great way to quantify right now, and that's small vessel riverbed mining. So you can see that these are all, relatively small boats. That's a dump truck. I mean, they're boats. But you can see that they have these pipelines that are piping sand that they have extracted from the riverbed onto shore, and then these tipper trucks, these dump trucks, then go in and take that sand and then take it off for continued processing. So we can map where these repositories are, but we don't have a great sense of how their volumes are changing through time. But we can map something else. We can map these tipper truck mines, these dump truck mines that I'm going to show in the next couple of slides. And so there's somewhere north of 100 of these sites between this barrage feature and the confluence with the Brahmaputra River down here. Like I said, we're skirting the border between India and Bangladesh right here. And I'll show a couple of examples of what this active river sand mining looks like in the next couple slides. So this is tipper truck mining. They call dump trucks tipper trucks, I guess. But what happens basically is on a seasonal basis, as I'll show in a second, these trucks go onto these active river mines and they kind of expand out and excavate out in this dendritic pattern, extracting sand that is then exported for processing. And so these features, at least where we have good imagery, are relatively easy to map in their spatial extent. And so basically what we did is we went through historical imagery in Google Earth and found the places that we could map them relatively discreetly. And we estimated the area that the mining activity is occurring over. And then I'll describe the methods for getting the depth that we use to estimate these volumes in just a second. But we can see how they expand through time. So here, I'll just go back to the beginning real quick. Okay, so note this is November 30th, 2015. In the December of the same year, January of the next year, and then March. So this is the time sequence of one mining cycle, where the total estimated extraction is 161,000 cubic meters at an average rate of 1,300 meters per day. I don't know real that is, because we're not, the time series that we have here is really limited to the clear sky imagery that is available in the historical data set of Google Earth. Okay, so we see that it starts over in November of 2016. So basically what we see is that the mining season runs from November into the spring, early summer. Then during the peak discharge season that's associated with both the monsoon and Himalayan glacial runoff, we see, of course, that the river levels rise, all of the riverbanks kind of redistribute, and the mines get wiped out. And then the next cycle, they generally emanate from the same location, and they go back out and they mine the river bars in whatever geometry they're redistributed in the next year. So we'll start again with this November 27th, 2016, and go through the 16-17 cycle. Okay, into the next cycle. Okay, so basically, this is interesting for a couple of reasons. First of all, from the perspective of each one of these individual mining locations, this would appear to be, relatively sustainable mining. You take a bunch of sand out of the system every year. The monsoon, the high discharge season comes in, replenishes the sand, and you do it again the next year. From a very localized perspective, that is ostensibly, seems like you're getting a sustainable supply of sand. So, like I said, we can map a little bit over 100 of them. And so what I'll show in the next couple slides is kind of how we're ballparking these volumes here. And so, like I said, we can map the spatial extent pretty easily. That's fine. But getting at the depth of excavation is a little bit trickier. And so what we can do is we can compare kind of the depth of excavation, at least in the initial stages of excavation, to the height of these tipper trucks. And so, we can get like a general estimate that here's the shadow of the actively mined surface here. You can see the shadow of a truck. I spent a lot of time researching popular tipper trucks in Bangladesh. Turns out they're about 3 meters tall. So we can say that at least in the initial stages, when they're initially excavating the river bars, the active extraction depth is probably a little bit over 3 meters. But as the mines expand dendritically out from this initial area, there are lots of these areas that are not mined to maximum depth. And as you would expect, perhaps as you're going towards the river, the mines themselves are getting less and less deep. They can extract less and less deeply due to water table or due to natural slope of the riverbed or so on and so forth. So we just kind of apply a general 2 meter depth here. And so, in some senses, that's probably an overestimate. In some senses, it's probably an underestimate, but it's just kind of what we're using as a representative excavation depth here. So for a couple of these places that we can map these features and get at extraction volumes, we have done so over a number of seasons that are kind of coded here in the bar graph. And the important thing that I really want to point out here is looking at kind of the minimum and the maximum estimates here. And so I'll note that the estimated Ganges sand load from previous work is about 41 million cubic meters of sand per year. 1% of that would be 410,000, 0.1% would be 41,000. And so we can see that the minimum estimates for a lot of these mines that we're seeing for some of these smaller mines are in the vicinity of that 0.1% of total load. And some of our maximum estimates are approaching that 1% of total load number. And so, obviously there's a lot of uncertainty here. Like I just said, we're very much generalizing how we're calculating these extraction volumes. But it does seem like some of these mines are extracting on the order of 0.1 to 1% of what is the total estimated Ganges sand load on a yearly basis. So this gets into this question of extracting from sinks versus extracting in transit sediment. And so a kind of common general equation here that is often used to describe sand resources in particular is your sand resource equals your sand stored plus your set in minus what you extract, over some period of time. And so, this may be true when you're thinking about a sedimentary sink where, there is no sand out term. But when we're thinking about this in transit sediment, we have to add this set out term or this sand outturn, because although, maybe what we are seeing is replenishment locally, that sand was then destined for a featured down system, in this case, the Ganges-Brahmaputra Delta. So when we think about what this means with respect to extracting sand at 1% or 0.1% of total load, when we add this set outturn, we can see that it actually doesn't take that many mines to basically completely erase your natural set in. So if mines are mining at about 1%, somewhere between 51 and 91 mines, you're removing 50 to 90% of your sediment. At this 0.1 number, it takes a couple hundred to 1,000 mines to basically remove all of your natural set in. And so it sure seems like this Ganges River system specifically is sitting right at this precipice where, like, along this stretch of the river, you're basically taking all of your set in out and putting it into this anthropogenic part of the source sink cycle. And so clearly this has implications for the evolution of the delta and in down system areas. Not necessarily explicitly because of this sand mining, but the Ganges-Brahmaputra Delta has been identified as one of the most at-risk deltas in the world. This paper by Zach Tessler kind of described both the natural hazard and the exposure, i.e. how many people are living or rely on the feature, and then the vulnerability of the feature, basically how bad the hazards that the delta are being subjected to are. And so the effective or the relative sea level rise in the Ganges-Brahmaputra Delta is just about the highest in the world. And obviously the sand that is in these rivers is needed to replenish that delta to keep up with the natural subsidence of the delta. So that in and of itself is a major sustainability issue, that these mines are removing the sediment that is needed down system, and you say, well, it's needed in human infrastructure, but there are these cascading effects of adding this anthropogenic sediment dispersal pathway and anthropogenic sediment sink to this natural source to sink cycle that has these features like the Ganges-Brahmaputra Delta that evolved this natural equilibrium based on the natural sediment flux that is received. And so adding this new human portion of the cycle has very, very major cascading effects. Okay, so then kind of getting into the question of how do we study this, and what are the important things that we need to define. Obviously your core sediment budget, sediment sources, residence times, and sediment dispersal pathways. And so, this seems pretty intuitively obvious. But a lot of the research that focuses on the environmental effects of sand mining often focus on things like local riverbank erosion or local nick point migration, kind of deepening or artificially widening the channel, reincision of the channel, these kinds of things. And that's all very important as well, but thinking about it from a broader systems perspective and thinking about both the ways that the natural sediment supply should be maintaining the system and the kind of integrated effect of each one of these perturbations in a down system direction is also very crucial in thinking about the broader impacts of anthropogenic sediment extraction on a natural sediment dispersal system. So Matt Malkowski, who is about to join the faculty in DGS, and I, along with collaborators from the USGS, have a project where we're going to do this type of study in San Francisco Bay. We actually just had kind of final negotiations today, and so hopefully we'll get this project started in the coming months, where we're basically going to do that, where there are still sand mines that are extracting sand and gravel from San Francisco Bay deposits, both here in Suisun Bay and down here near Angel Island, just north of San Francisco. And so we're going to go in and I'm happy to talk about the kind of hypotheses that we're testing and the methods that we're going to be using. But we're going to actively go out and do another one of these projects relatively soon. Okay, so in the last couple minutes that I have, I want to talk about the human basin. So this is just the Google Earth 3D model of Shanghai. And so thinking about, we have this new anthropogenic step, or this new human step in the natural source to sink cycle, and we have these new human sedimentary sinks. A city is a basin. The degree to which this sediment is being extracted from natural systems, or the degree to which this system is made of new sediment that's being generated, that's an interesting question. But basically, you're looking at a sedimentary basin in a certain sense. Oh, my dog's about to start barking. Hey. And so, because this is still sedimentary material, we can still study it in a certain sense, like we would study a sedimentary basin. And so, thinking about the kind of more interregional or international sediment dispersal pathways that are now part of this source to sink cycle. Generally speaking, coarse sediment, sand and gravel, is heavy. It's expensive to transport. So generally, sand and gravel production and relocation and use is a relatively local phenomenon. But there are some examples of countries that either don't have a whole lot of this natural resource, or countries that just need a lot more than they can produce. And so this is particularly true in Southeast Asia, where there's a lot of regional dispersal, human dispersal of sand and gravel resources. So anytime that you have a situation in which you have high demand that is not being met adequately with supply, you have the incentive to generate illicit or illegal supply networks. And so this is particularly true throughout the developing world that is building a lot of new infrastructure. And so kind of highlighted here in red are a dozen or so countries in which there are known kind of well-developed illicit sand supply networks where sand is being extracted either in an unregulated or explicitly illegal fashion and being used to meet supply or meet demand in areas that cannot supply it for themselves. And so the question here then becomes, how is this regulated and how is this monitored? Well, generally speaking, currently it's monitored with satellite imagery, what I just showed you in the Ganges River, or it's kind of monitored with kind of boots on the ground, looking for dump trucks full of sand coming out of places that they shouldn't. But what if we can apply provenance analysis, basically, these common techniques in sedimentology that we use to study natural sediment dispersal patterns? Why can't we use them to study these illicit supply networks as well? So, in the same way that this is done in ivory with DNA signatures, or it's actually done in certain parts of the drug trade, looking at in this case, strontium isotopes and heroin. But these materials carry with them a compositional signature derived from whence they were derived, that we can use to say something that goes beyond having to see the sediment being removed and explicitly tracking it with our own two eyes. So this is probably familiar to anybody that is working on sedimentary basins, but basically you've got these source regions that are producing your sediment. They each have some compositional signature. Now, when we're adding our human dispersal vectors, now this is sediment that is being carried into human systems. So construction aggregate is processed relatively minimally. It's washed, it's size sorted, but at least the aggregate that goes into concrete and so on is not heated, it's not crushed. There's basically nothing that's changing the mineralogical composition or the chemical composition of the individual sediment grains through any of these processes. So, maybe we have to modify conventional provenance analyses to account for these biases that are imparted by size sorting and washing. But basically, there's no reason why we couldn't, treat a city center the same way that we treat an ancient outcrop with respect to doing provenance analysis on it. And then, of course, there are unprocessed uses like land reclamation. And so then the question is, interesting, but why? And so again, it gets back to the development of these illicit sand supply networks. And so one of my collaborators on this is a Norwegian researcher who does material flow analysis in Norway. And he always jokes, how do you know where a dump truck full of sand in Norway came from? Well, you ask the truck driver, and he'll tell you where it came from. That's not true in a lot of the world. And it's also difficult if that sand is already in concrete in a building or was put into concrete in a building 50 years ago. And so when we're thinking about what we're calling fingerprinting the illicit supply networks, that information exists in perpetuity. We can go in and do provenance analysis on a chunk of concrete, now or 1,000 years from now, and use that information to say where it came from. And my collaborators on this that know more about the material flow analysis side of it also think that there are applications for networks that are not illicit networks in terms of thinking about examining material flows and stocks in times before there was a great record, or in areas where nobody thought to take a record, or thinking about the effect that regulations are having on where sediment is actually coming from and entering into these built environment stocks. And so again, I like to just end with this, that the natural source to sink sediment dispersal cycle now no longer ends in natural sedimentary sinks for a lot of the world's sand and gravel. It now ends in human sedimentary sinks. And this is illustrated down here. These are those supply and demand values that I showed earlier in the talk, where these are kind of the natural sediment supplies, and these are the demands shown at a linear scale this time, as opposed to a log scale, as it was shown in that last figure. This was at the bottom, but anyway, when it's shown at a linear scale, you can see how significant this new human basin, this new human sink part of the source to sink sediment cycle is. And I think that there's a lot of really interesting stuff that can be done here from a basin analysis or a kind of a sedimentological perspective. All right, that's all I have to say. So I would be very happy to take comments and questions and just generally discuss this topic.
Yeah, any questions, feel free to unmute yourselves and ask it out loud.
I can ask a question. Have you tried to do a DZ analysis of like a concrete sample yet?
Nope, not yet.
I think it's funny because people always talk about, like sweeping up, whatever's left on the mineral separation room floor and seeing if you can pick out people's different sources, but yeah. This is like a better.
Well, yeah. So yeah. I mean, you bring up some really good points here. There are a couple of things. First of all, it turns out that this is not the kind of thing that proposals get written on very often. And so figuring out like how to fund something like that has been a non-trivial hurdle to this work so far. So my collaborators on this come from a bunch of different backgrounds. And so we're currently in the kind of funding search phase for a lot of this, and figuring out the best avenue to get something like this funded. And then, you bring up another good point with the detrital zircon specifically, and thinking about what the method to use is. Like, is detrital zircon the method to use? I mean, based on, so Dr. Reza Farhan of civil and architectural engineering at UT is our kind of material science concrete expert that we've been working with, and she sees no reason why any of even the accessory minerals would be washed out. They'll be fractionated, right? Like we can't just compare KDEs or PDFs the way we would in a sandstone. But I don't think that any methods are off the table. It's just a matter of finding the right method that isn't just answering, oh, that's interesting, but is actually cost effective.
Yeah, I guess my mind, I saw that you used like the very start of the Romans like source to sink figure. And my mind just immediately was like DZ, but like,
oh yeah, no. Yeah, totally. I mean, if DZs work, that'd be great.
Yeah.
Yeah.
Yeah, very cool.
Thank you. Anybody else?
Hey, Zach, I have a question
Hey,
or a
what's up?
comment more.
Yeah, of course.
Yeah, thank you for the talk. I like it. Yeah. So first time when I heard about this problem was about illegal, illegal digging, and actually was in international trafficking. They were saying the sand from Southeast Asia is going to UK for for different construction. So
Yeah.
so I'm thinking maybe if from your question or worrying about who's funding it, maybe will be some, government agencies that will want to do it, or environmental,
Yeah.
non like NGOs and things like that. That
Yeah.
they
Yeah.
might care. But my question is that, you identify the problem, and it seems that you know how to get to it, but can you also like propose a solution or something? I mean, people will not stop building concrete things.
Yeah.
Will accelerate probably. And
Yeah.
I heard, Norway, I heard that they start building really tall, apartment buildings out of wood to cut on the energy. They say it's going into concrete, but I think that's you can do that at the large scale.
Yeah.
Do you have an idea to what to propose them? Just to carry it out of places where it's easier, like Sahara maybe, or other places.
Yeah, right. So yes, there are solutions to a certain extent. So like I kind of said earlier in the talk, countries like the US and Canada and a lot of countries in Western Europe are now using pretty exclusively crushed rock materials. But as you might imagine, crushing rock, particularly crushing rock to the fine aggregate size, is a lot more energy and labor intensive than it is to just go get sand out of a river. So one of the things, and this is something that Dr. Farron is particularly active in working in, is thinking about recycled uses. So basically, anytime you're tearing down a concrete building, you don't just ditch the concrete. You use the concrete and the aggregate in the concrete and recycle it into the next generation of concrete. And it turns out you don't even necessarily have to completely disaggregate it. Chunks of concrete itself can be the aggregate material. There's also work on generating synthetic aggregates, but that seems, I'm not a material scientist. I don't know if that's reasonable or not. But at a minimum, I think that the issue of understanding the residence time of the sediment and thinking about whether the sediment is in a sink before you take it out is really the crucial sustainability issue here. If you're going to keep extracting natural sediment from natural deposits. But yeah, that's and yeah.
So it's just a comment on that. So your solution would be to actually, through your projects, to point them where the less impact reservoirs of sand or other sources will be.
So based on a better understanding of the source-to-sink sediment cycle in the given system that you want to extract sediment from, find the best part of that system, or determine if there is a part of that system from which sediment can be extracted with minimal down system perturbation. Yeah,
I can see that if you point it to them, but people have to follow probably. Southeast Asia, everyone is living by a river where it's easier to get.
Yeah, so there's another really interesting implication here is that a lot of the current understanding of the effects of removing sand from these systems is like I said, the local riverbank erosion, the local deepening of channels, migration of nick points, stuff like that. But what I think is more interesting to think about in a certain sense is the long-term implications of when are you going to see the actual peak of the perturbation. So, there's evidence that suggests that in systems that are dammed, you're impounding sediment behind the dam, but the river actually, the relatively sediment deprived river downstream actually then re-incisors the river. And so when you get to a certain distance further downstream, you're actually seeing a relatively comparable coarse grained sediment load to what you would have been seeing without the dam, just because the river is down cutting and kind of resupplying itself with sediment. So if in these systems, like I showed in the Ganges example, if you're removing all of the sediment load and then the river is then re-equilibrating by increasing its downstream incision and increasing the sediment load that it is deriving from its own older deposits, at the delta, you might not even see the largest magnitude perturbation for hundreds or 1,000 years until the river can no longer resupply itself with sediment due to channel incision. So I think that even if you stopped mining in a lot of these areas, it would take the system quite a long time to re-equilibrate to something approaching the natural state of the system.
Thank you.
Yeah, thank you. Okay, we got something in the chat. Let me. Oh, Kat. Okay. Oh yeah, thanks, Kat. Yeah. Okay. So this was something that I was going to touch on with Cornell's point as well, with respect to government agencies. So I gave a talk on this at GSA this fall, and the FBI contacted me. There's a forensic geology lab at the FBI. And their head geologist contacted me to talk about methods and method development. So talking to them, they were saying that there are actually like some National Institute of Justice grants that fund work like this or could fund work like this. So yeah, I was. Yeah, definitely. I mean, I don't think the issue is that nobody will fund this. I think that the issue is that I don't know, like I don't write proposals to the types of funding institutions that would normally fund this. So it's kind of a discovery process. Yeah. Yeah, so I mean, this is like a sidebar to a sidebar, I guess. But the forensic, like the job of the forensic geologist at the FBI is fascinating. They were describing how like a field office would just send them something and say, hey, where did this come from? Like a piece of glass or like some soil off of somebody's shoe. And it's like really just like really fundamental, basic geoscience stuff. Really interesting.
Wow, that's awesome. I had no idea that was even a job.
Well, there's only like 3 of them.
Yeah. Funny. Well, we're just about out of time, but that was a really cool talk. I feel like I learned a lot about something that seems fundamental, but I knew almost nothing about. So it seems like it's important to our society. So
thanks. Well, next time you're walking down the sidewalk, look down and you're just walking on sand.
Yeah. Awesome. All right. Well, thanks so much for joining us, everyone. Yeah. Next week is spring break, but then join us for the week after that. And yeah, I'll see you then. Bye-bye.
Thank you, everyone.
Thanks so much, Zach. This was cool.